So this is, I mean, and Ulf will get into when he talks more about the orthogonal and complementary techniques. He'll show some examples where you have to be careful in batch measurements and make sure you're doing some sort of other measurement that has better resolving power, like chromatography, for example, to make sure even in certain formulations where you have surfactants or you have sugars, things like that, that those aren't contributing to the overall intensity. So it's good to check everything, but DLS is a good screening tool, just to get an initial idea of what's happening in your system. Of course, another application for this is melting points, or I guess it's not melting points, it's dynamic light scattering melting points, where you see the onset of unfolding of the protein with a given temperature. You'll see that in the size change shoot up, and this is obviously different for different proteins. So this is just another way to use a quick, easy batch measurement to get another idea about your sample itself. And of course, you can correlate these with DSC, which we'll see later. So it's just another way to get another piece of information out of the measurement you're making. So we talked about this earlier, obtaining molecular weight. Well, you actually, in a lot of cases, don't need to go through a involved concentration study with static light scattering to get molecular weight. If you're working with a globular protein, you can obtain molecular weight from the size that you're measuring by dynamic light scattering. Okay, so this is a plot of a series of different proteins at different molecular weights. They're all globular. They all follow in the same trend. This model here, and the numbers used here, then you can analyze subsequent proteins that are in globular in structure and obtain a molecular weight just from the batch DLS measurement. So there's different ways to get to your molar mass measurement: static light scattering, dynamic light scattering using models, and static light scattering off of an SEC column. So all these techniques can be used together to see how consistent your numbers are. So batch dynamic light scattering, some pros. It's an absolute measurement from first principles to get size, hydrodynamic size of your protein. Low volume and concentration requirements, so you're not restricted to a small range here. It has a large size range that you can make these measurements under, as Kevin was alluding to in that figure from his thesis from long ago. You also get polydispersity, of course, PEI, and particle size distribution. And it's sensitive to higher order aggregates due to the weighting, R to the 6. So you'll be able to see some of these aggregates in your batch measurement show up, and you should be able to resolve some of those out. So you'll get an idea right off the bat if the formulation you developed with the excipients and the stabilizers you put in there are working in the formulation. Some of the cons, it does have low resolution, and that's just kind of the sticking point. That's just one of the features of a batch measurement. But that's why we're here tonight to talk about other techniques we can use to validate the DLS data, or for DLS to be used to validate other data. The question that this gentleman asked was about the intensity weighted distribution. You have to be careful with that. You're gonna see something's there, but you have to be careful with that conversion to see how much of that is actually there. Typically, when you see that something's there, you need to go to the next step and try to fully characterize that with another technique like SEC or AUC. Okay, so the next topic, if we're moving right along here, again, you see the similar figure with these similar static and dynamic light scattering images here. So from the same type of system, you can look at zeta potential, or charge, or potential at the boundary, at the hydrodynamic boundary of your protein. And how we do this is looking